In this section, we're going to look at general design principles underlying the programmable GPU shader cores. We'll start with a stereotypical high-performance CPU core, and look at what we need to adapt to make it more efficient for the types of data parallel workloads processed by GPUs. The algorithms that most consumer software runs on a CPU tend to be relatively serial due to the nature of the problem being solved. Lots of dependent control plane logic where the later behavior depends on the result of earlier execution. This limits parallelization opportunity for most problems, so thread counts tend to be modest. Tens of threads, even for software which can be multi-threaded. The serial nature of the problems being solved means that making applications run faster requires faster single-threaded hardware. Adding more CPU cores in parallel won't have the desired effect if the application doesn't have the necessary parallelism in the first place. In addition, faster CPUs need fast access to data. Any data accesses which need to read from DRAM may have hundreds of CPU cycles of latency to get a result. If this happens too often, the CPU may simply run out of work to do and start to stall, waiting for the data to arrive. This diagram shows the bare essentials that every processor must have. There must be some form of instruction fetch, which loads the instructions that tell the hardware what processing needs doing. There must be some form of register storage to hold the current working set of the program. There must be a processing pipeline which actually performs the arithmetic and logic computation needed. These pipelines are multiple cycles long. Each computation is split into multiple phases and executed over multiple cycles. The reduced amount of logic per phase allows higher CPU clock frequencies to be used. Pipelines of 5 to 10 cycles are not uncommon. As pipelines get longer, it is common to have instructions with dependencies on earlier instructions that are still in flight. Stalling and waiting for them to complete would significantly reduce performance, so a number of tricks are used to unblock the stalled instructions. The first of these is result forwarding. Results of earlier instructions can be forwarded to later instructions before the result is actually written back into the register file, shaving a few cycles off the result latency. The second of these is branch prediction. For control flow, we include hardware which tries to guess the result of the conditional branches, and we will issue execution on the predicted path. If we guess wrong, the hardware has to back out, canceling the issued instructions on the wrong path, and restart. However, if we guess right, we can keep the pipeline full. Most instruction streams have fine-grained parallelism in them, instructions which can run in parallel as they have no data dependency. This allows us to increase performance by doing multiple things in parallel. The downside is that instruction sets are generally specified as a serial instruction stream, so we need to add some additional hardware to manage the parallel instruction issue. For a modern processor, simple in-order parallel issue can't find enough parallelism to keep the wide instruction dispatch busy. So, high-end processors generally include some form of out-of-order execution, which allows the processor to find parallelism present in a large window of instructions, and issue those instructions as soon as they are eligible. Many processors use speculative execution, filling in idle units with operations which might be useful. For example, executing both the if and the else of a conditional block, and keeping the result that is actually needed. Memory fetch from main memory is expensive, so processors will generally include some form of prefetch unit, which aims to guess where future data accesses are going to go and proactively pull that into the CPU data cache. And of course, CPUs tend to have large level 2 or level 3 caches, allowing large chunks of critical code and data to be kept close to the core in high-performance local storage. All of these orange components that we've added to the CPU design help that single thread run faster, but it's adding a lot of silicon area and a corresponding power efficiency drag. Can GPUs do something different to avoid them? One concept from CPUs that is useful is the concept of vector processing hardware. Most application processors have some form of vector instruction set, such as the ARM Neon instruction set, which expose vector operations to software. For the cost of managing a single instruction, we get multiple data processing operations, amortizing the energy cost of the instruction control overheads, and making the overall processing more energy efficient. This is an idea that we'll come back to, as energy efficiency is what the GPU really needs. GPUs solve very different problems to CPUs. We have a problem space with a very high thread count. hundreds of thousands of vertices and millions of fragments, all executing in a local thread of control. Performance of single threads in the workload isn't that important. It doesn't matter if a specific vertex has a result latency of 20 cycles or 20,000 cycles. What matters is completing the whole frame as fast as possible. High performance is achieved by building the most energy-efficient hardware that we can, and exploiting the parallelism inherent in the problem domain to run many energy-efficient hardware units in parallel. Let's start with the simple vector core, much the same as our CPU starting point, but with a vector data path. The data path is still multiple cycles, let's say 10 for the sake of argument. The first type of change we can make is to make the shader core multi-threaded. In this design, we would issue the new instruction for thread every 10 cycles, interleaving instructions from all 10 threads to fill the pipeline. This increases the latency to complete a single thread by a factor of 10, as it only gets to use 1/10 of the performance at a time, but the overall throughput of one instruction per cycle is maintained. This change has multiple immediate advantages. Firstly, we no longer need special issue logic and speculation to find parallelism in the instruction stream of a single thread. We have parallelism inherent in the problem, and can instead fill parallel units by issuing instructions from multiple threads. Secondly, we no longer need result forwarding or branch prediction. By the time instruction n for a thread executes, we can guarantee that instruction n-1 has completed, so results and condition codes are guaranteed to be available. This just leaves the memory-related units to worry about. Having 10 threads is enough to hide our logic pipeline latency, but nowhere near enough to hide the latency round trip to DRAM, which is typically around 150 GPU clock cycles. CPUs hide this using clever prefetch and big data caches. For a graphics workload, a data cache is never going to be big enough. The working set for a frame of rendering is typically over 50 megabytes of data, which is just way too big to keep hot in an on-chip cache. Instead, GPUs go massively multi-threaded. Rather than having 10 threads, what happens if we have 1,000? We need 10 threads awake and ready to run in order to keep the processing pipeline busy. But we can use the other 990 to form a pipeline of memory requests to DRAM. As long as one thread has data and is eligible for execution, we can keep the data processing pipeline busy. With this change applied, we can remove the need for speculative data fetch and large caches. We have built an architecture that can tolerate cache misses and DRAM fetch latency, by exploiting the huge multi-threading opportunities the problem domain allows. We like the vector hardware of SIMD instructions, as they amortize control overheads, but the SIMD instructions themselves can be problematic. SIMD exposes vector instructions to each thread. So, the program being run must contain a vectorizable problem to take advantage of the hardware. Some aspects of graphic shaders are certainly SIMD friendly. We have X, Y, Z, W vector data, and RGBA color data. But modern graphic shaders are using increasing amounts of code which cannot pack out to Vector 4 hardware units. One further change is therefore to keep the vector hardware, but switch to an SPMT, single program multi-thread programming model. In this design, we run multiple threads in lockstep, each thread running the same instruction and seeing one lane of the vector hardware. The thread groups running in lockstep in this concept have multiple names. Warps, wavefronts, Vulkan subgroups, they all mean the same thing. The good news with this approach is that the vectorization width is no longer dependent on the program being run, provided we have a problem with lots of threads. We can further increase the warp thread count to 8, 16, or even wider to further amortize the control plane cost over the more data processing operations. The downside of this approach is the impact of branching. What happens if two threads in a warp want to execute the if, and the other two want to execute the else? In each issue cycle, every lane in the warp must run the same instruction. So, effectively, the hardware will have to run both the if and the else, with the lanes that are on the wrong path being masked out. In this example, we therefore only get 50% utilization out of the hardware. This is called warp divergence, and shader algorithms should be designed to avoid it. The final aspect of the programmable core is a set of fixed function accelerators, that handle many of the domain-specific instructions that form parts of the graphics shader programs. Common units include interpolators for varying data, texture decompressors, texture sampling and filtering units, and frame buffer blending units for alpha transparency. These units are more energy efficient than emulating the behavior in general-purpose instructions. Around the outside of the programmable core, shown in the blue background box here, are additional fixed function units which handle creating new threads and retiring threads as they complete. The fragment frontend, for example, will handle rasterization, early ZS testing, and hidden surface removal. The tile wrapback unit handles all of the tasks needed to get completed tiles back to memory, including multi-sampling resolves and frame buffer compression. When you put all of this together, you get what we call a shader core. But it is worth knowing that there is no standard definition for what a shader core actually contains, and it does vary across vendors. In summary, GPUs are energy-efficient, domain-specific accelerators designed to accelerate extremely data-parallel workloads with high thread count. This is driven by the desire in mobile to get the prettiest possible graphics out of a system inside the sustainable 3-watt thermal budget. This video concludes Module 1 of the Mali GPU's Essentials training. In the next module, we will explore the Mali GPU family, and start introducing some techniques that you can use to improve graphics performance.